For the stuff that we've been looking at, like these first three styles of problems, your forces were really quite like constant, for lack of a better word. Like in the example the question I just did from your homework, this force pushing up the ramp is going to be the same the whole way through. But we've looked at other things, i.e. springs, for example, where the force required to stretch them changes depending on how long they've been stretched. So it's really easy to stretch a spring a little bit. Like that doesn't take a lot of work. But for every little bit you want to go further, it's not like the same amount of energy every time. You've got, not the same amount of force every time. You've got this increasing amount of force, for example. That's one example of the kind of force where you need to use graphical analysis to actually go ahead and calculate the work, because the force is constantly changing. So we use force displacement graphs to find things like this. So I'll put a note here. This is most useful for variable forces. i.e. springs. So here's an example. I've got this graph here. On one side, I'm labeling the force. On the other side, I'm labeling the distance. So we said that before. Work is equal to a force times a distance. Well, if I'm taking values of force and multiplying it by values of distance, what am I doing on this graph? Yeah, here it is. Yeah, I'm finding the area, you bet. So the area on a force displacement or force distance graph is the work done for any given chunk of this graph. So I'll just do two simple examples of this. If I want to find the work done moving an object from 2 to 6 meters, all that would be is I just want to find this area. From the 2 meter mark to the 6 meter mark, what's the area of that shape? And we've done stuff like this before. When we were back looking at a displacement, velocity, acceleration graphs, to go from displacement to velocity, we found slopes. To go from velocity to acceleration, we found slopes. But to go the other way, to go from acceleration to velocity and from velocity to displacement, we were finding areas. So same idea here. What we're going to have to do is break this thing up into smaller shapes to find the area for this chunk. What are those shapes going to be? Take a look at that compound shape there. We can break this thing up easily into what two shapes? Yeah, Lena. A rectangle and a triangle. So we're going to go like this. This is definitely lower than that line. So I'm going to have this orange triangle right there. And this lovely blue rectangle here. And those are the two shapes I need to find. The sum of those two areas is going to be the work done for whatever this force is acting over that distance. So what is that value right there? Because we need that. Is it 1.4? Because this is going to be 1.5, right? 1.4? Sure, we can call it 1.4. Does anyone have huge issues calling this value 1.4? Okay. No one's going to fight you on this here day. So 1.4 it is. What's this value right here? What do you want to call that? Sure. Incidentally, Lena, that is what last semester called that value as well. Last semester would have argued with here day a little bit. They called it 1.3 instead of 1.4. So my values are going to be a little bit different than they were. But I mean, fundamentally, without better data, this is what we have to do. So this is what we've got. Let's go ahead and find the area under this graph between 2 and 6 to figure out the work done. Now, the area is going to be equal to the triangle plus the rectangle. The triangle is 1/2 base times height. The rectangle is just going to be base times height or length times width. Same thing. And so we can plug this all in. The 1/2 is going to be there as a 1/2. The base of the rectangle is from 2 to 6. So that distance is from 2 to 6. That's 4. And now what is this? Is this what you said? The 2 point, that's the height of the rectangle, or the height of the triangle rather. That distance is from 1.4 to 2.75. The height of the, I think Lena just said it, is 1.35, or 2.75 minus 1.4. To that, we're going to add the rectangle. The rectangle is just 4 wide by 1.4 tall. And that's going to equal something in the neighborhood of 8. Times 4 times 1.35 should be in the neighborhood of 8. Plus 4 times 1.4. 8.3 joules. And that's it. When you're given a variable force, you need to graph it to get an accurate representation of what's going on. That's the sum total of my lesson today. I have nothing else for you. Because the way the rest of this breaks down, I could do power today too. And that's so much work I'm giving you for homework. It's a lot of work. But you guys could do a lot of work, right? You know what? That was really short. No, this isn't Christmas time. This is 2 weeks up to Christmas time. If you want, I can give you work over the homework over the Christmas break. So here's my dilemma, guys. My dilemma is I have just enough time to get you guys up to the review for this chapter for the Friday before the break, which means your test would be on the Monday week or the Tuesday we come back from Christmas break. That is not ideal for so many reasons. So if you let me cram in another portion of a lesson today and then work better than you normally work on the work that I'm going to assign, yes, I'm not talking to you specifically, Lena, but as a general rule, you guys kind of dawdle when I give you homework. I would like to get this test done before the break because otherwise that would suck. So I think I'm gonna try. It's only 125. We got this. You guys are great. I have great faith in you. This is the last mandatory unit. There's 3 bonus units that I can choose to do a couple of. Okay, we're doing it. Flip power. This lesson, here we go. So, in addition to talking about work and as a force times the distance, a change in energy, kinetic energy, potential energy, all that kind of stuff, what we can do is we can take it a smidge further and say, okay, given the amount of work that you've done, however you've done that work, change potential energy springs, change potential energy with gravity, given an object kinetic energy, pushed an object with a force over a distance, however you've done the work, we can look at the power now that you've been able to output. Power, all power is, whether you call it well, there's a bunch of units for it, but however you measure power, power is just defined as how much work you've done in a given period of time. That's it. If you do the same amount of work as someone else, that's great, but if they do it quicker, they've exerted more power. They are a more powerful individual than you are in whatever criteria we're calling that. So, power is equal to your work, however much you've done, divided by the time it took you to do that work. Interestingly enough, though, one of our definitions for work was a change in energy over a change in time. Or, one of the other definitions we had for work was this is going to be equal to a force times a distance divided by time. But what's distance divided by time? This is just velocity. So you can also think of power as being equal to a force times the speed, which is weird. Now, it's important to remember that what kind of velocity is d over t? This is your average velocity or constant velocity. So you've got a few ways now to measure power. Power is measured in well, we have a couple units for it. If you're considering power as measured in change in energy divided by time, or even over here, work divided by time, this is a joule per second. Work and energy, both measured in joules per second. This one is interesting because this is a force times a distance divided by time. So if you look at this, power is also measured in Newton meters per second. Newton meters per second. But there's another famous dead guy who did a lot of work in this area. And we use his name to override joules per second or Newton meters per second. Anyone know his name? Watt. 1 watt is equivalent to 1 joule per second or 1 Newton meter per second of energy done over time. So power is also referred to as horsepower because horses used to be a thing. I mean, horses still exist, but we don't use them in the same way we used them before. And 1 horsepower is defined to be, this is a number you're going to need here in a little bit, 746 watts. It's a very specific number. So 1 horse could produce 746 joules of energy every second, is what 1 horsepower means. Yes. So like yes, horsepower, and it is this. 1 horsepower when we talk about cars is equal to 746 joules per second or watts of energy. 200, yeah, so my Toyota Corolla XRS has 170 horsepower. My Corolla. McLaren F1. Sorry? HPS. So to give that some context, my Corolla has 170 horsepower, just the model of Corolla that I have. For anyone who are into F1, any F1 watchers? Yeah, did you watch the race on Sunday? So good. I missed the first 10 laps, and that's when everything happened. Oh, I was angry. My boy went from last to third. Leclerc, man, I was so stoked. Anyway, Lando Norris won. Lando Norris drives for McLaren. That car that he won in has 627 horsepower. For those of you who watch F1, who are into F1, those are the fastest regular use cars on the planet, arguably the most powerful. 670 or 27, 630 approximately horsepower in those kinds of cars. So this is the range of horsepower you're looking at. So that number, 627 horsepower, 627 times 746, you're looking at 467,742 joules of energy released by that car every second, which is wild. Just an absurd amount of energy. So, a couple examples of how this gets applied. If a 30-kilogram object is lifted 20 meters straight up in 2 minutes, what was the power used? There are two ways you can handle this. Boom, vertical line. Let's draw it out. It doesn't say that it started on the ground. It doesn't say, it ended 20 meters above the ground. It just ended 20 meters higher than when it started. So let's just assume, because we can do that wherever it started is what we're going to call zero energy. So here's our object, and I'm going to measure from the bottom of the object. I don't know if it's on the ground. It doesn't matter that it's on, whether or not it's on the ground. I'm just going to call that h equals 0. And then this thing gets raised. We're going to call this h equals 20 meters. So there's a few things we have to assume. We have to assume that the thing was raised at a constant rate. Otherwise, we have no way of knowing what's going on here. So assuming this thing was raised at a constant rate, the applied force has to be what? What forces are acting on this box? Gravity. And if the rate at which the box is moving is constant, what can you tell me about Fa and Fg? They're the same. Might be useful in a second. So, two ways we can look at power, because that's what we're looking for. What is the power used to do this? Power is either equal to work over time, or, on the other side here, we're looking at power equals FV. Let's look at this one first, power equals FV. We know the force applied to do the lifting has to be equal to Fg. So this is going to become FGV, which is just going to be mg times v. And we can find v. V is equal to distance over time. So this is just going to equal the mass times the velocity times the distance traveled divided by how long it took. Let's pause there for a second. Let's go back and look at the other side. Power equals work divided by time. Work is equal to a change in energy. So power is equal to a change in energy over time. What energy are we changing about the box? It starts at rest presumably, it ends at rest presumably. So what energy are we changing about the box? What kind of potential energy? Gravitational potential energy. So this is going to be equal to the change in gravitational potential energy. That's just going to be equal to potential energy gravitational final minus potential energy gravitational initial. And because I said that the initial, the height was 0, what's PE initial going to be? 0. Oh wait, this is all divided by time still. So this piece right here is 0. So this is just going to be mgh final over time. These look awfully similar, don't they? How high was the box raised? How far did the box travel? Over here. 20 meters. In both cases, the time is 2. In both cases, we've got an m and a g. It doesn't matter how you tackle this thing. The end result is going to be the same. So this is just going to equal the 30 kilogram box times the 9.8 acceleration due to gravity times the 20 meters the thing was moved divided by, time always needs to be in seconds. So 2 meters is actually how many seconds? 120. So power, big P, is going to equal what? What's that value? Sorry? 49 watts. So less than an old school light bulb, because those were 60 watt bulbs. That's fun. Questions about anything I've done? Okay. Next example. How long does it take a 2.0 kilowatt kettle to do 50,000 joules of work? So I got a kettle here. It's empty, so I can look at the bottom. Just to give you an example, this is a 1.5 kilowatt kettle. So 1,500 watts, 1,500 joules per second. This is a 2 kilowatt kettle. That subscript K, that's kilo. So 2.0 kilos is going to be 2,000 watts. Just to clear up some of the notation to start. And we want to know how long it takes to do 50,000 joules worth of work. Now, we have no context for what 50,000 joules worth of energy or worth of work means. Next week, we're going to look at converting this into a temperature. 50,000 joules worth of work is going to change the temperature of water by a particular amount. That's Monday's lesson. Monday, Tuesday, next week. But for now, this is meaningless. I don't know what, well, you don't know what 50,000 joules of energy on a kettle is going to do. So, but let's find it. We want to know time. We know the power output of the kettle. We know the energy that it's produced. How long does that take? Well, that's relatively easy to find. Power is equal to work divided by time. And we can plug all these values in. A 2 kilowatt kettle is the same as 2,000 watt kettle. We want it to do 50,000 joules worth of work. We want to know how long that's going to take. So now isolating this thing for time, I'm just going to multiply time up and divide 2,000 down. The time is going to equal 50,000 divided by 2,000. That 0, and that 0 cancels. 50 divided by 2 is 25. And time in physics is always measured in seconds. So a 2,000 kilowatt kettle is capable of producing 50,000 joules of energy, which sounds like a lot, in 25 seconds, which doesn't seem like a lot of time until you shove your hand on it, on the element, and then that's an entirely different story. And like I said, next week we'll look at, well, what does this actually mean? How has the temperature changed if this is the amount of energy produced? Okay, one more example. An 80 kilogram person can run up a flight of stairs in 2.1 seconds. If They gain 1.7 meters in height. What is the power of the person? Well, here's what's going on. You've got a person. Here they are on the ground. Oops, sorry. Here they are on the ground. There's a bunch of stairs. You, this person, have gained some height. In this case, 1.7 meters. So we're going to call the bottom height 0. And we want to know what the power of the person is who has done this. Gained the 1.7 meters in height in 2.1 seconds. Well, power is equal to work divided by time, which is equal to a change in energy over time. What energy is changing for the person? Potential gravitational energy. So PEG, this is going to be change in PEG over time. That's just equal to potential energy gravitational final minus potential energy gravitational initial, and if we call, divided by time. And if we call that bottom floor or bottom step 0, initial potential energy is, if they start at 0, initial gravitational potential energy is 0. So this is just going to equal mgh over t. We have an 80 kilogram person running up against gravity, going up a height of 1.7 meters in 2.1 seconds. This person is that powerful. What's that number? Just for fun, Lena, I'd like you to take that number in your calculator and divide it by 746. What'd you get? 0.857? 8507. 0.8507 what? Horsepower. Taking your power in watts and dividing it by 746 will give you your equivalent horsepower. So this person is as powerful as 85% of a horse. You guys have 40 minutes. Your task, first, I want you to flip a couple pages to the Stairmaster Lab. Here's what you guys get to do. Y'all are going to find your horsepower. You're going to run some stairs. Don't do what happened in Mr. Clark's class a couple years ago. Girl passed out doing this. Because she hadn't eaten all day and then she ran a bunch of stairs. I think she did it like 4 times. She passed out. So we're going to ballpark this because this scale is not totally accurate. That's okay. You need your mass in kilograms. What you're going to do is this. In groups of, I would recommend groups of 3 or 4. Just so a few of you all aware of what's going on in that. You need to determine the mass of each student. I recommend groups of 3, but determine the mass of each student. If you need to do 4, you got space down there. Names for all your data, masses, and you're going to run stairs twice. I want you to do 2 time trials And what you're going to do is we're not going to loop the stairs. We're not going to do the whole all the way up. You're going to run up one straight flight of stairs from A landing to A landing. I don't care if you touch every stair. I don't care if you're just like you're starting from rest. Person says go, and he starts the stopwatch. And you stop when the person hits the top step. When they're like both feet are on the top step. First time, every step. The second time, you're allowed to skip steps. You need to measure the height of one stair. Figure out how many stairs you have, because that'll give you the total height that you climb. After you've got your time trials, calculate the work done and the power of each student for both time trials. And then you've got some questions on that. You're going to start with that. Find each other's horsepower and overall power with watts. That's what we're going to do. You're going to start there. And then I've got some questions on it. So, get yourself in threes or fours, however you want to break yourselves up. And start away. There's stairs. Just go with the stairs. Go easy. We have landing to landing. Corners, one straight shot. On your mark, set, go.
So time 1 is every step, time 2 is...
Yes, I just spoke earlier. Time 1 is one touch every step. Time 2, you're allowed to skip. No, doesn't matter. Make sure you're using the kilograms on the small numbers. I would recommend you guys use these because the bottom of the ruler is actually 0. You use these to measure the height of one of the stairs. Remember, you're using the inner set of numbers. Okay, so as you guys are completing this thing, I think I said it before all of you came back tomorrow. I do want you to, tomorrow, not today, tear out this page. I'm going to take it from you guys. Your homework, in addition to that, is the rest of this, 11 to 18. There's questions there about power, questions there about change in energy. And if you flip the page, there was a set of questions, because none of the homework I gave you had anything to do with springs from Friday. There are 10 questions here that are all about springs, exclusively springs, potential energy related to that. And there's a graphing one in there as well. So what I'd like you to do is take a look at these questions, numbers 1 to 10 as well. So you've got a chunk of homework. We have class before lunch tomorrow. But I want you to take a look at that. In a perfect world, you don't have to get the questions I just asked you. Those do not need to be done for tomorrow, but ideally for Wednesday, because Wednesday we're going to start our bungee lab, and you need to have looked at these elastic potential ones before then, if Wednesday's lab is going to make any sense. So you do still have a little bit of time left. There's about, I think, 3 or 4 minutes till the bell goes. Use this time. Tomorrow I want you to hand in your horsepower lab. We'll discuss it a little bit. And then you've got this homework here too. So when the bell goes, you may also go. Have a great day, and you've got some work to do.